Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi. So thanks for coming. So it's my great pleasure to have Zvonimir Rakamaric visiting from Utah, and with his student Shabo, who's in the audience. And Zvonimir is well known to us. He's visited us as an intern a few times, and he did work that is still being done both here, like the Q verifier, in Havoc, and he does the SMAC tool, which is pretty popular to compile source programs down to Boogie and Z3. So a lot of people are using his tools. And today he's going to talk about some new directions that he's been pursuing. So welcome.
Thanks a lot, Shuvendu. Yeah, it's certainly nice to be back. So we can keep this informal, clearly. There isn't a lot of people, so feel free to stop me at any point. We can discuss various things and so on. So yeah, today I'll talk about this ongoing work, which is collaboration with also Shuvendu, which is on using SMT-based verification for reasoning about approximations in programs. And before I start, this is my wonderful group of students. We kind of recreated one of the photos that you maybe saw before. And if you want to find out more about other things that we're working on, you can go to this web address. And again, apart from the work I'm talking about here, we do lots of other stuff related to software verification and so on. We do analysis of floating point computations. We are working on this SMAC tool that Shuvendu mentioned that translates LLM-IR into Boogie tool flow. We started working on security and safety of kernel modules and protocol stacks. We still work on analysis of concurrent programs such as pthreads, OpenMP, GPU, and so on. Kind of dabbled a little bit in Android malware detection, and also in automatic testing of Java and NASA software. So if you're interested in any of these, I'm still here for 2 more days, so just let me know and we can talk about it in more details. So the work I'm going to cover in this talk is on approximate computing, and it's done with a bunch of collaborators. Shabo is here, Shuvendu as well, and then at Utah, part of this work is done with a PhD student, Very Fun, and my colleague Anesh Gopalakrishnan. A brief roadmap about this talk. I'll motivate approximate computing first with a couple of slides, and then I'll introduce our approach and also why we think it's a good approach. And then I'll talk about in much more details about how we verify safety and accuracy of approximate program, as well as relative termination. And we'll see how much time we'll have in the end. I do have this somewhat separate work on the synthesis of floating point approximations. And like I said, we'll see if we'll get to it. And a little disclaimer, this is all work in progress, so some of the things are maybe not completely fleshed out, and the experiments are a little bit preliminary, so feel free to ask any questions, and if you have feedback, even better. That would be also great. Okay, maybe I won't spend too much time on introduction. We don't have too many people in the audience. So yeah, this is a pretty well-known graph that illustrates how hardware was scaling starting from 70s to 2010. And clearly, in the first few decades, this is a log scale. So everything was kind of growing exponentially, which really spurred this computing evolution that was happening around that time. And Microsoft certainly profited a lot from this growth, and other companies as well. And then around 2004, 2005, certain things started slowing down. In particular, clock speed that we were on which improvements we were relying on before. And that's when companies such as Intel decided to switch to multi-core processors. Today, this free lunch that we've been all enjoying for many years is pretty much over. So what broke around 2004 was then our scaling, which was saying that as transistors get smaller, their power density does not change, so you can keep increasing frequency. And then, like I said, that's when hardware companies decided to switch to multi-core, which is, it kind of worked, but it is a partial solution because you have to then write parallel programs and so on, which is not always easy as just speeding up your chips, sequential execution on your chips. And then Moore's law, which talks about doubling of transistors that hardware manufacturers can put on chips. It seems that it's slowing down as well. So there's some recent news that Intel is postponing 10 nanometer chip making process. And on top of that, you can't really even power up all the transistors that you have on chips these days. So there's this concept of dark silicon that talks about which transistors can be powered up and which not, and so on. So we have to be careful about that as well. So that's kind of the lay of the land of what is happening in hardware these days. Now, if we look at applications that are really popular these days, we can see that lots of them are, I said, fuzzy. And because data, maybe that they take is fuzzy, or we don't need really totally precise answers and so on. And there is many applications that fall into this category, ranging from machine learning and data analytics to cyber physical systems, graphics, and so on, games, sensors in mobile devices. So these are all applications that potentially don't need completely correct results because they deal with fuzziness of the world around us anyways. And this slowdown of advances in hardware combined with this fuzziness of applications that we want to run on this hardware has led to emergence of approximate computing. And the main idea about it, behind it, is to embrace this fuzziness by introducing controlled trade-off of accuracy to improve performance or energy efficiency. So instead of performing completely correct computations, maybe you relax them a little bit, which can cause that you improve performance or energy efficiency, but you're still happy with your results. So that's the main kind of idea behind approximate computing, in my opinion. And it's been up and coming area. In the last couple of years, there's been a bunch of papers in this area. And 2 years ago, a year and a half ago, we also started working on some of the problems in this area, which is quite interesting. So there is a bunch of ways that approximations can be introduced. I listed some of them. There is more than this, just to give you some intuition of what these approximations are. So a colleague of mine, for example, is working on approximating memories. So they're playing with tuning memory controllers to be able to lower refresh rate in DRAMs. So that way you preserve energy, but you might get more bit flips in the values that you read and so on. So there is a trade-off there. Then there were papers on relaxing loop computations by doing loop perforations, which means you just skip, every few iterations of the loop. Recently, there has been work on neural processing units, where you train your neural network to replace a part of your program, and so on. So those are kind of approximations that people have been working on. And then motivation behind our work is that introducing this approximation has to be done in a controlled way, ideally, because there's this fine line between overly aggressively approximating your code, which can lead to then really bad results on the output, or being very careful and doing just very conservative approximations, and then you don't really benefit a lot from them. And to facilitate this, I think the programmers need automated techniques and tools to explore different approximate computing trade-offs, and so that they can play with these different approximations and see what is good enough for their purpose. So in the literature, people kind of split up these criteria based on which you judge whether your approximation is good or not into a couple of different categories. So the first one is, and the most basic one is safety. So safety just says that approximations should hopefully not introduce any catastrophic failures, like null pointed references or things like that. The second one, and that one hasn't actually been mentioned a lot in the related work, is termination. So ideally, the approximations that are again introduced should not cause non-termination. And finally, we have quality results. And this is, again, typically split into two subcategories. The first one is accuracy, which talks about difference between precise and approximate outputs. For example, approximate output is at most 5 away from your precise output. And the second one is reliability, which talks about probability that approximate output is precise. So an example would be my approximate output is correct 90% of the time. And in the other cases, it might not be correct. And so far, our work has focused on these 3 criteria. So on safety, termination, and accuracy. We still haven't really touched reliability. That's potential future work area. Okay, so our goal, like I said, is to enable this rigorous exploration of approximate computing trade-offs. And we want to do this using automated formal techniques for reasoning about approximations. And we decided to do that after we studied the related work literature, where we noticed that current techniques that people use often lack in either rigor, because what often happens is that to assess approximations, other researchers just do relatively simple dynamic analysis and sampling. So there is no really any kind of rigorous proofs that the approximation is really good enough. Or sometimes they lack in precision, where something like a type system can limit what you can really express and what you can reason about when it comes to approximations. And finally, recently, there were several techniques that proved upon precision and so on, but they suffer from not really being that much automated because they heavily rely on the interactive theorem provers, and in particular, it's Coq. We want to apply automated differential program verification for reasoning about these approximations. And the idea is to compare original and approximate program, while at the same time we encode the relay specifications as differential assertions. So these properties that I was talking about, safety, accuracy, and so on, can be encoded as assertions that talk about precise and approximate programs. And I'm sure you've seen talks about differential program verification before from Shwendu. It's similar to equivalence checking for hardware, but it goes beyond equivalence, which is why it is nice for approximate computing, where what you're trying to prove is not really equivalence. And our hope is that we'll achieve precision and automation using SMT-based checking and invariant inference. We know SMT well as invariant inference, so we hope that this work will improve upon something like using Coq. Okay, so this was brief intro motivation. The one I want to talk about next is how we verify safety and accuracy criteria. And we do it using differential verification, which is based on mutual summaries that relate pre and post states of two procedure versions. And Shuvendra published algorithms that can check these mutual summaries modularly by constructing this product program. And by doing that, you can use any off-the-shelf program verifier or inference engine, which is really nice. So we can leverage Boogie and Houdini and Z3 and apply all of that technology to check this criteria that I listed for various approximations that people care about. I don't know if I should really talk about mutual summaries and things like that. How many people have seen these talks before? Okay.
There might be people on the ResNet.
Okay. Okay. So let's try to briefly go through it. So mutual summary is a general form of writing differential specification. So if you have two versions of a procedure, then you can write a mutual summary which relates inputs to outputs of both of these procedures. So this mutual summary is saying if x's are the same and this global variable g in one version is less than or equal to g in the other version, and x1 is less than or equal to 0, then globals at the output, one is less than or equal to the other one. So it connects these two procedures, and it specifies, it talks about a specification over these two procedures. And it includes parameters of both of them and globals on the input and output, and also return value. Okay, so these mutual summaries are used in the algorithm called differential assertion checking, or DAC, which enables modular reasoning and invariant inference. And the steps of DAC are to convert this differential verification problem into a single program verification problem. So you have these two program versions, and you smash them together into a single program. And you have to do it in a very strictly prescribed way. And once you have this product program, then you can leverage any single program verification technique to infer invariance. And once you infer the variance, you can just again verify this combined program using anything you have that can check single programs. So now I'm certainly not going to go into details of this, but you can find it in Shuvendra's paper. So this is the construction of the product program. So you have two program versions that are taken as input. In this case, they're just two procedures, F1 and F2, and which invoke H1 and H2. And this is the product procedure for these two procedures. So there are a couple of things to note. It's one procedure that captures the effects of both of these. It performs these calls to H1 and H2 because these bodies of these procedures are being inlined here. And another important thing is that in the end, it also calls product procedure for H1 and H2. So this is kind of the key point, because now you can stick in those mutual summaries at these call places, and you can actually prove them and so on. Without this, you can't really do that, and then you cannot infer pre and post conditions. So you cannot basically infer mutual summaries. So yeah, key part of the translation is, I think, this, and there is a kind of quite a lot of bookkeeping around it, which I'm not going to go into. But this is how the product program construction works. And then once you have that, you can run something like Houdini inference engine on it to infer mutual summaries. OK. And there you go. This is exactly what we do. We can do invariant inference. It exploits structural similarities between two programs by just restricting the kinds of invariant we can generate to simple differential predicates. And differential predicates, it means that they talk about variable versions from the two programs. So they're in the form of x and then some operator x prime, where x is from one program version and x prime from the other one. And this operator can be simple things such as equality, less than or equal to, and so on. So these are the predicates or predicate templates. And then we use Houdini to infer Boolean combination of these predicates. And that happens completely automatically once these predicates are provided, or predicate templates are provided. And I should also note that SymDiff automatically generates a bunch of these. So you don't even, for many examples, you don't even have to go in and provide any kind of templates. But if you need something more complicated, you have to help it out a little bit. OK. So yeah, the key benefit of this is that you can reuse the infrastructure. So once you create a product program, this box here is what you already have. So this is, for example, Boogie and Houdini, which is really nice. You don't have to develop really anything special for discharging these product programs. And we leverage this a lot in our work. So the implementation of our tool that discharges these approximate programs and their differential properties is based on this encoding. We did have to extend it with automatic inference of richer invariants in the sense that users can specify additional predicates, and we can infer a Boolean combination over predicates and not just conjunction. So that was needed for some of our examples that were, I guess, a little bit more complicated than what SymDiff has seen before. OK. So this is a tool flow. There is an original program, an approximate program. It's fed into SymDiff. Potentially, we need a few manual predicate templates. From that, the product program is generated, and then Boogie and Houdini are run on it, and hopefully it can be discharged using that. So like I said, we start by verifying two criteria. One is safety, and in our particular case, what we checked is control flow equivalence, which basically means that for the same input, both programs execute the same sequence of basic blocks. And this criteria is actually quite important when you're introducing new approximations, because you often don't want to break this guarantee. Typically, it means that weird things are happening if your two versions are not control flow equivalent. And this is mentioned in other related work papers as an important thing to work on. And we also have a couple of benchmarks where we checked accuracy. And in this case, this accuracy criteria came from related work that used the same set of benchmarks. And one example would be that output computed by approximate procedure is within some prescribed distance from the original procedure output. OK. A little bit about control equivalence. So we came up with this, I think, pretty clever way of encoding control flow equivalence using unindependent functions. So we have this global variable called summary. And in every block, we update it with a new value, which is just f of summary and block ID, where f is some uninterpreted function. And for every block, we generate unique block IDs. And by doing this, in the end, we just have to compare these summary variables in the two versions. And that actually works really well, and I think it's a quite nice encoding of contraflow equivalence. I haven't seen it before. I mean, it's pretty simple, but pretty nice. The original implementation actually was storing things in an array. Every block was stored in unbounded array, which was kind of pretty dumb and not as scalable. So this was a nice kind of update to that.
So when you look at the invariants, then you're just saying things like summary on the left equals summary on the right, or something like
Yes.
that. So you don't have to worry about
Yes.
the F functions aren't going to appear in the.
Yes.
Sorry, where did the havocs go?
Havocs?
You said approximation introduced using the havoc statement.
Okay.
I don't see any havocs.
Yeah, so let me show you. They'll come up soon. Yeah, I didn't put it in this example, but they'll come up soon. Yeah, good question though. Here is a concrete example, and next slide we'll have havoc. So we have a couple of examples where we check contraflow equivalence. This is one of them. So the main thing to focus on is this part. So this is just a recursive procedure that iterates over this array, global array, and it searches for a character that is equal to x, and then if it is, then it replaces it with y. So it's basically replacing x with y in this array. And it terminates when either n is reached or array is set to -1. So it's your basic kind of replace character procedure. We do have to turn everything into tail recursive procedures. So you would usually write this using a simple loop, but here we encoded it using recursion. So that's the original version, and approximation basically scrambles whatever was read from this array. So this is the havoc that introduces approximation. So we just, whatever is read from this array, we completely scramble it. And so we have two versions now, one without havoc and one with havoc. And we want to prove that contraflow equivalence, that they're contraflow equivalent. So that's our goal.
That's an interesting question, right? But I mean, you had the ternary operator there. So do you consider the control flow to pass through the ternary operator or not?
That is a very good question. No. Yeah. But yeah, very good question. So yeah, no, we don't count this in contraflow. We do count this if. But yeah, good question. And so, yeah, what is kind of interesting about this example? It's kind of not trivial to do. It's not easy to do it using just simple taint analysis. So if you notice here, this scramble variable is flowing into this array, which then flows back into this if condition. So we tried simple taint analysis on this, and it will just say, everything is tainted. And this happens because it can't really reason precisely about array segments. You can imagine extending it with some kind of additional abstract domain that would kind of keep track of actual array segments and so on, but it gets pretty tricky. And using SymDiff and so on, we can actually do things like this.
But can you mention what this havoc is trying to mimic in terms of approximation?
Oh, so yeah, we usually start with boogie programs, so I sometimes forget to relate this to real world. That's what happens when you work on formal methods. So it's trying to mimic reading from an approximate memory. So array stored in approximate memory, you read from it, and you can get anything essentially. So that's one kind of little example. That's probably our smallest one. So we verified the control flow equivalence for this example using SymDiff and the tool flow I showed you. And verification effort is almost completely automatic. We had to just manually provide one relatively simple predicate template, which was actually talking exactly about these array fragments. You kind of have to know whether you are ahead of I or not. So that's the predicate we needed. So that's example where we checked safety criteria. Switching to accuracy, we took a few examples from this PLDI 2012 paper that was proving these acceptability properties for approximate programs using Coq. And these are pretty small examples. I guess when you're using Coq, you can't really, well, okay. So here is one of their examples. It's highly abstracted search engine called Swish. And this procedure is supposed to print out on the screen or decide how many search results should be printed on the screen. So it takes this max R and N, and num R is the number of search results. So it has this loop where, it's either bounded by max R or N, and it just keeps incrementing it, and then it returns num R. So very, very, very simple and abstract version of something that you could maybe see in a search engine. And then here is the approximation. So the red lines are what introduces approximation. It's a little bit more involved and interesting than we had it before. So we are not just completely scrambling this max R variable, but rather we do this in a more controlled way. So what this is saying is actually that if max R is less than 10, then don't change it. And if it's greater than 10, then it can be anything as long as it's still greater than 10. And the idea behind this approximation is that the server can kind of throttle how many search results it's presenting to the user. So if the load becomes really high, then it can, instead of presenting 100 results, it can present, 20 results. And you always have to present at least 10. So that's the idea behind this approximation, and it was taken from that paper. So we had to also specify, what we actually want to check. And this is an example of this distance kind of criteria, where we are saying if the inputs are the same, then the outputs should be related by the same relaxedQ function. Okay, so yeah, a little bit about the verification effort again. So we managed to discharge this by providing manually 4 relatively simple predicates. Carbon et al. Had this proof in Coq that had around 330 lines of proof script. So, the examples are pretty small, but I think we really are kind of improving up on this. And the surprising thing is also, and I discussed this with Mike, I mean, we are proving exactly the same properties. So it's not that we changed anything or removed anything. Exactly the same example, exactly the same property, and we can do it pretty automated way.
I remember back when reading that paper that one of the tricky things that Mike had to deal with was sort of reconvergent control flow. Like the proof framework is supposed to handle cases where control flow is affected for a little while, but eventually you come back to the same place. Okay. And you want to say something about the values that exist in both programs at the same time. Okay. Did you ever run into that in the example?
So I haven't seen their examples that actually have that. Okay. Like maybe it's a different paper. The examples in this paper are all kind of following this pattern. It's not even control flow. They actually
if they had built the proof framework necessary for it, but haven't found an example that exercised it. Too.
Could be. I will have to think about this. It's not. So you're saying you want to allow that it diverges in a certain part, and then it converges back.
Right, and you still have it a reasonable thing to say, like x1 and x2, when those things might be the product of totally different control flow.
Okay.
But now you're at the same place, and so the same variables are available.
I see. I mean, we can play with certainly with where you want to track it and where you don't want to track it by putting these updates or to summary or not. So I'm not. Anyways, maybe we could think about it. Yeah, that's a good question. Okay. So yeah, we do have a little bit more extensive relation than just these two examples. And we have a couple more for control flow equivalents. Selection sort is pretty interesting because it has some of the similar flavor to replace character. There is this updates to array that don't really influence control flow. And the key to be able to handle these examples is that you need to precisely capture these array fragments. So we're kind of focusing on examples where doing just simple taint analysis is just not good enough. And we handled other examples from this Carbon's paper. There's 3 of them.
What's the error model for things like the selection sort and bubble sort?
It was always just havoc. And havoc, typically it was reads from arrays.
On array reads.
Yes.
Okay. Why would that preserve control flow?
So I remember, I forgot, I actually remember selection sort. So selection sort kind of, oh no, in selection sort it's actually right. Yeah, it's right. It kind of has this index going from end of the array towards the beginning of the array. And control flow only depends on and everything after the index is sorted.
Yeah.
So the
But you have the condition somewhere that says if x less than y, then swap.
Yes, but this condition only talks about elements that are before I. You go from 0 to I, and that's where you're applying this condition. Once you are behind I, that doesn't influence control flow anymore. So basically, when you are writing your largest element kind of at I, you can actually write anything you want. You can write completely scrambled value because I will move, and then your control gets preserved.
Bubble sort.
I can't remember how bubble sort. I think there was somewhere like a similar behavior. It depends on how you implement it. I think we just had 2 loops.
I don't think we have the exact phenomena that would show up in bubble sort.
Because it seems like, if in bubble sort, if you're just testing and swapping, right? And if that's an if then else, and then you have a different control flow path depending on the value of array reads.
Yeah. I can't remember what.
But I guess bubble sort, you always have that loop. You have the nested loop, and then whether or not you swap depends on the values. But the control flow is the same. It's always going to be n squared.
No, but we can't swap as actually. It is a control flow. It is because it's like if it's less, then swap. Otherwise, don't swap. So it is counted as control flow, and I can't recall. Do you know Shabo maybe? Okay.
But so clearly, you're not always interested in fully preserving control flow, right? Even in your little example with the ternary operator, you don't care which way you go around the chart. So somehow the user has to specify at what level of granularity.
Yeah. So we can. That's what I was saying to Adrian. We haven't played with this. We didn't, I guess, think about it. But I think Adrian even asked this before. So we can actually, given our coding, we can pretty easily kind of, based on some kind of user input, either annotate the blocks with those updates to summary, or we don't annotate them. If you don't annotate them, then those are just not analyzed. So you can just put these control flow tracking updates to key points in the program, and everything else will still work. Yeah.
Can I
It does that with approximate types, right?
Yeah, so we could do something like that. Yeah. If it's approximate and it flows into a block, then maybe you tag it as kind of important. If it's not, then you don't tag it. Yeah. Okay. And here are some experimental results. So we managed to verify all of these. And this is actual verification. Our initial effort was actually unrolling, which was kind of much easier, but we weren't that happy with that. So here we actually generate invariants and perform like full-blown verification. Okay. Okay. So yeah, let's talk a little bit about relative termination. And this is the one I'm particularly excited about. And we only started working on this maybe 2 or 3 months ago, but yeah, we're getting some traction, and I think it's a very interesting direction. Okay, so this termination criterion, people don't really talk about it that much in approximate computing community. Although, if we talk to somebody like Adrian, people think that it is, important. So the way we specify it is that, 2 programs satisfy this relative termination criterion if a precise execution terminates for a given input, then its approximate version should terminate as well. So it's not absolute termination. If your precise version does not terminate, then you don't care what your approximate version does. And there are some advantages to doing things this way. First of all, we avoid proving absolute termination. I believe that proving relative termination is typically easier because the kinds of invariants you need, and I have one example, they're actually not that involved often. And we know that coming up with good ranking functions can be quite hard if you want to prove absolute termination of just a single program. And I also do think that it is more meaningful in the context of these program approximations, because typically you want to reason about 2 program versions, and you want to see how your approximation influences the original version. So I think it's probably a more meaningful thing to check when it comes to program approximations and so on.
So control flow preservation would also imply relative termination, right?
No, I should have said that.
Okay.
Yeah, okay. I'm missing, that's a great question. So everything that I talked about so far assumes that they terminate. So this is actually another advantage that I should add here. Another advantage I should add here is that it actually assures that whatever you proved in the previous step really holds, if you can prove relative termination.
Because you only actually test that summary is right on termination.
Exactly.
So if I just wrote while true, then
yeah. If you block somewhere, you don't even get to the actual assertions and so on. Okay, so you don't really prove it. Thank you, Ken. This was very good. I should have had that sentence on the slide. So yeah, another great advantage of this.
I have a major concern. Has your mother-in-law seen this slide?
My mother-in-law? No.
I mean, I'm sorry. The first. I mean, when it's relative safety and but when it's relative termination.
Oh.
not termination.
I know. I'm sorry. That's just the way my brain works.
Thank you, Tom.
Termination.
Do you have any particular relative in mind?
I was just wondering if he did.
I love my mother-in-law.
You look good. Me too.
And she's visiting my wife right now, actually, okay. Which is also great because I get a chance to travel more. Yeah. Okay. Another thing to change on this slide. So 2 changes.
I'm not sure.
That's a good one, Tom.
Only he will see that.
Okay.
No, I can take the blame. The mutual termination was taken. So we had to go for the next logical one.
Do you also use relative termination? You do? Okay. So it was not me who invented it. I wasn't sure anymore whether I...
Oper had coined mutual termination. So I had to.
You should have warned Shumenda before.
I didn't even know it came from Shiva.
Mutual termination also sounds gory.
Yeah, that's true.
termination, I guess. Yeah, so we can, the construction for proving this termination, relative termination, is kind of somewhat similar to product program construction that I already talked about. So let me go a little bit. Instead of having mutual summaries, you have relative termination condition that enables you to prove relative termination, and that you also have to check. So this is like precondition. And so this checking is based on product program encoding that was published in CADE 2012, 11. With so Schwendo and a bunch of other people published it, and it's a pretty neat encoding for checking this relative termination. So you have to introduce this uninterpreted sum relations that capture input-output behavior of functions, and then you assume that nested calls that are being made, recursive calls or nested calls, you assume that they terminate, and you can do that using axioms that refer to the relative termination conditions I talked about in the previous slide, and these sum relations. And then you stick in assertions that check that callees also terminate, and discharge these assertions relies on this assumption. So let's just see a little bit how the construction looks like. So this is a very simple example. Simple loop increases x by 1. This is approximation. It's kind of what loop perforation basically does. Instead of increasing by 1, you increase by 2. You skip every other step. And so we want to prove that this approximate version, relatively terminates as compared to the original version. And the first thing we again have to do, we extract loops as tail recursive procedures. So this is the main kind of part, and here is the recursive call. So nothing special really happening there, and we do have to. So these are the summary relations. So they're being assumed at these two places. So this one belongs to loop, that one belongs to main. And the main thing we want to prove is termination of loop. Okay, so here is how the construction works. So this is your product procedure, where you inlined the body of your first function, and you inlined of first procedure and the body of a second procedure.
You mean x1 plus 2 there, right?
Oh yeah, no, x2 plus 2.
Plus 2.
Yeah, sorry. So this is a typo. So this should be the body of the second procedure. So it should be x2 plus 2, x2 plus 2. And you have to assume your relative termination condition. And in this case, it's that x1 has to be less than or equal to x2. Right? If, let me think a little bit about this. I always have to pause here. So if if x2 is less, then it could happen that the first program exits right away, but the second one has to iterate. Okay, and this is this axiom that I was talking about. So this axiom is saying that if relative termination condition holds and loop 1 terminated, then there should exist R2 such that loop R2 also terminates. And this is encoded using these summary relations.
How come that's an axiom?
Yeah, because this is assumption, and you check it here. So there is, I guess, induction happening here. And it took me a while to actually understand why this actually works. But yeah, so this is saying your nested calls are terminating. And then you want to prove that, at the current level, you are terminating as well. If that makes sense.
So there is a meta argument on top of this, why this is sound. But yeah.
So this assertion here proves that you're terminating at this level. So this is encoding. Any other questions?
So here, loop R1 means that it possibly terminates on input X with output X1 with output R1 over here.
Right.
Okay. So we're proving
there is some execution from X1 to R1.
Right. So yeah.
So does that mean that our loop R2 could be also possibly non-terminating? I mean, is it?
So if loop R1 terminates, then loop R2 has to terminate as well.
So at least if there is at least one execution that terminates in R1, there is.
Right. So if loop R1 is possibly terminating, then loop R2 is possibly terminating.
Yeah. Right.
I'm just saying if it was non-deterministic choice in the loops. Right?
Yeah.
Oh, I see. Okay. Okay.
I just wanted to understand this.
Right.
This
So
semantic.
usually you would strengthen this with a mutual summary that R1 is deterministic, and then make it,
anyhow, it's I like this equality. I think it's a very nice equality. There is a lot of quantifiers though, which can get tricky. Okay.
So the only one that's tricky there is the assertion.
Yeah. Okay. Sure. Please go. Actually, we'll meet today, so then I think I'll bug you a little bit about this. we can prove kind of some examples, but then some other ones gets a little bit hard. And I worked with quantifiers a long time ago, and I never wanted to work with them again, but I am. So yeah. Okay, so yeah, so now we have this kind of two encodings, right? We have the deck one where you are actually invoking these combined procedures and where you can infer invariants. And we have this K encoding which I just showed that we can use to prove termination, but it's not really clear how to do invariant inference here because these product procedures are actually not being invoked anywhere. Instead you have these axioms. So to be able to do automatic verification even in this context, then we came up with a solution which iterates between these two encodings. So we generate invariants using deck encoding, and then we transfer them into K encoding, and we check for termination, and we can kind of iterate this. So if you look at the tool flow, very similar, except now we generate two product programs using both encodings, and then we push invariants from one into the other, and then try to prove termination. So Shabo implemented this part. And we've been playing with this a little bit. We have a preliminary evaluation. I think we have 2 or 3 examples. So this loop perforation that I showed and replace character. Same example, we just proved termination. And it's pretty automated. Again, we only need one or two manually provided predicate templates. Quantifiers are kind of tricky, and we do see non-termination and things like that. And we've been working on this in the previous couple of days. So that's termination. I mean, I like it. In the approximate kind of approximate computing community, there hasn't really been a lot of effort on doing anything like this. So I think it's pretty novel, and we'll see how far we can push it. And I'll skip floating points in the interest of time. We have some basic work on synthesizing floating point routines with lower bit width of floating point operators and data and so on, which I think it's quite promising. You can save a lot on performance and data bandwidth and things like that. And we do it in a rigorous way using our tool that we have for reasoning about errors of floating point computations and so on. And I have slides on that, but like I said, I can talk about it offline. Yeah, about this work. So we show that we can apply this automated differential program verification as it's implemented SymDiff for reasoning about approximations. We also showed that these mutual summaries that I talked about can quite naturally express several types of relay specifications that are useful for proving in this context. And we show that we can, improve precision automation over previous approaches because we leverage SMT checking and invariant inference, which is almost completely automatic. And by combining all of this, we proved that it is feasible to apply, all these verification techniques that we're all familiar with and that we all love, or most of us do at least, to the domain of approximate computing. So I think I ran out of time, so I'll stop here. And like I said, I can talk about floating points offline if anybody's interested. Thanks a lot, guys. So, yeah, any other questions?
You just need some more examples now.
Oh, I do have future work. And the first point is more benchmarks. Yeah, benchmarks are quite challenging. We did get some from later work literature, and Adrian has been helping us a lot to try to find more benchmarks. So hopefully, in the next week or two, our benchmark set will be much larger. And then, yeah, we can always try to improve predicate generation further and so on, kind of the usual stuff. Yeah. Anything else? Okay.
Let's thank Sonimir.
Yeah. Thanks a lot for coming.